Okay, moving right along. Unit 3, Day 5. We're going to look at just a quick review of compound interest when you're compounding money continuously. And then we're going to go into graphing logs and exponentials, just a quick review of that, and then the always fun task of properties of logarithms. Okay, so this one, a bank account compounds continuously. The interest rate is 2.1% after 12 years. You have $27,200 in the account. It wants to know the initial amount of the account. Okay, so if you recall from previous classes, you have a formula. A of t, or the amount after a certain time, is equal to p times e to the rt power. So this is your continuous growth rate. Or sometimes you see that p, or that initial value, the principal, written as a sub 0. So sometimes you see different terminology in the PFAs. So I'll try to keep you apprised of everything I might know that might be coming up. Okay, so in this problem, we know our final amount is $27,200. I don't know my beginning amount. I'm going to go ahead and use the capital P for that. E, my rate is 0.021. And that was there for 12 years. So I want to know what the original amount was. So I am going to just go ahead and solve for P. So I have 27,200 divided by e to the 0.021 times 12. So essentially that is the problem you have to solve to get your beginning amount. So one thing you can do with your calculator is go ahead, you could do it in this form. If you use your fraction key, that would be perfectly fine. I would probably go ahead and calculate the decimal for the denominator. And then I would go back and just take 27,200 divided by, and then go up and capture that decimal. So you're using an exact value instead of a rounded off number. So if you do that correctly, you should get $21,141.06. So over the 12-year period, you gained what, about $6,100. That's not terrible. Okay, so quick review of graphing exponentials versus logs. So first thing I'll do very quickly is graph an exponential. So we have f of x equals, I'm going to use base a to the power of x. So I'm going to put some values in a chart. I have x and f of x. For exponentials, you have a domain of all real numbers. You have a range. If you remember, we have a horizontal asymptote at 0. So 0 to infinity. We have a horizontal asymptote at y equals 0. And we have a y-intercept of 0, 1. Notice the forms of all of those things. So since my domain is negative infinity to infinity, I'm going to start with negative 1, 0, 1, and 2. Okay, so I don't know my base. This is a general parent function. So a to the negative 1 is 1 over a. A to the 0 is 1. That's where your y-intercept comes from. A to the first is just a, and a squared. So I can graph those points. The thing I won't do is just label the y-axis since we don't know what a is. So I know I have a point here at -1 and whatever 1 over a is. Well, 1, my y-intercept is going to be a little bit larger than 1 over a, so that's going to be there. Then I'm just going to go up here and put this as 1 comma a and 1 comma a squared. So this point right here is 1a. This is sitting here at 1. This point right here is 1 and 1 over a. I have a horizontal asymptote at y equals 0. And that exponential graph for exponential growth, parent function looks just like that. Okay, so now we're going to look at a logarithm. So for a log, or to find the inverse of an exponential function, I'm going to take my original function, I'm going to change my f of x to y equals a to the power of x. I'm going to switch my x and y like I do for inverses. And then I'm going to change to a logarithm, log base a of x equals y, or f inverse of x. So here's the inverse of that exponential function. So if you think about the way inverses work, one way to find the points is to just switch the x and y in your original function. So if I go back to my original chart that I have here, f of x, all I have to do is switch those. So I'm going to do f inverse of x. That should be a little -1 so you can see it. Sorry. F inverse of x. There we go. Okay, so I'm going to do this in a different color. All I'm doing now is I'm taking these points and I'm flipping them because x and y are going to switch places. So I have 1 over a, -1. I have 1, 0. I have a and 1. And I have a squared and 2. So if we look at our domain and ranges, these are going to switch because domain is x, range is y. So I can switch places there. My horizontal asymptote is going to become a vertical asymptote at x equals 0. My y-intercept is going to become an x-intercept at 1, 0, which is right here in my chart. So my domain is the range of the exponential function, so 0 to infinity. My range is all real numbers. Okay, so again, just think about how inverses work. X and y switch places, even for your characteristics for domain, range, horizontal, vertical asymptotes, and x, y intercepts. So this is going to be my log graph. So I have a vertical asymptote at 0. I have an x-intercept at 1, 0. And then I have these points. I don't really know what the value of a is, but I know down here, 1 over a, I'm going to be sitting here at -1. 1, 0 is already on my graph. A and 1 is going to be here. Then if I go out here to a squared, which is going to be a little bit larger, I'm going to be sitting at 2. So this graph for the log looks like this. So this red graph is log base a of x. This first graph, or the black one, is a to the power of x. If you also remember Inverse functions reflect over the line y equals x, just sits right through there like that. So there you have the graph of an exponential and its inverse, which is a logarithm. Okay, so again, quick review. I know logs are not everybody's favorite, but unfortunately for you, I kind of like them. All right, so we have a couple things that we have to review. I know if you had Algebra 2 in the spring last year, I taught this, and if you had me, I think Miss Morris did the same thing. We covered logarithms the very last 4 days of the spring semester, which we were all in distance learning. So you may or may not remember these things that we went over, but I'm going to review it with you. All right, so we have a thing called change of base, which I think you actually have to know for the ACT and or the EOC, so you might pay attention to this. So if I have log base A, log base A of B, we know we can put that in our calculators just as a different base. But if you do need to change bases, you can change it to base 10 by just doing the log of the argument, which is the B value, over the log of the base, which is A. So that would be changing to base 10, because remember base 10 is the common log. Or you could actually change it to a natural log. So the natural log of B over the natural log of A, which would be natural log. Which is base E, if you remember. You could change it to other bases if you wanted to, but honestly, I don't really see the need for it. Unless you're in a higher level class and you have a bunch of logs with different bases, you might have to do that. All right, so here's properties of logarithms. Should look a little bit familiar. So for this one, this is called your product property. So we can take logs and we can expand them and we can condense them. So if you see two logarithms with the same base, you can condense it into one logarithm by just multiplying those arguments or that xy. If you have a log that's already been condensed and for some reason you need to expand it, you just take it and change it to an addition of two logs. This is called your quotient. Which if you're dividing the argument, then you can switch it to subtraction or vice versa. You can also think about your exponent properties because they're inverses of each other. If you were taking a squared times a to the third, where you're going to add those exponents, which is a to the fifth. So that goes with this, where you take that argument, and if it's multiplication, then you add those values. Here, if you were taking a to the fifth divided by a squared, you subtract and you get a to the third. So those properties go hand in hand with your exponent properties and your log properties. This one right here is a handy one. It's called the power property. So it allows you to take the exponent of the argument and just bring it out front. And then you have multiple logarithms. It just makes it easier to calculate with. All right, so we're going to do some expanding and condensing of these logarithms, and some of them get a little bit complicated, so you need to show some steps in order to get to the final answer. Okay, so on this one, I see that we're expanding it. So I have a subtraction, or I have a division of the argument, so I know I'm going to have to subtract. And I also have a radical, which is going to confuse things a little bit. And I have powers. So I have a lot of things going on this problem. So you're going to need to show some steps. First thing I see is I can actually simplify my x squared and my x to the fifth. and change that to x to the third, which is going to make things a little bit easier. Okay, so the first thing I'm going to do is apply my quotient property. So I'm going to take that argument and I'm going to expand it to a subtraction problem. So I have log base 7 of the numerator, and I'm going to put my x first and my y second just to get my alphabetical order, minus the logarithm of the denominator. The x squared is gone. And if you think about the square root of z, I can change that to an exponent, which is z to the 1/2. So now I can take this piece of the puzzle. I can apply my product property. So I have log base 7 of x to the third. Product property allows me to add my two logarithms. Log base 7 of y to the third minus log base z, or log, I forgot the 7 there, sorry. Log base 7 of z to the 1/2. Okay, so my last step would be to use my power property and bring those exponents down front. So I have 3 log base 7 of x plus 3 log base 7 of y minus 1/2 log base 7 of z. So this answer is completely fine. Or you could actually factor that 3 out of there if you wanted to, and get 3 log base 7 of x plus log base 7 of y minus 1/2 log base 7 of z. Oops, forgot the log. So on the answer key for these, I've given you a couple options for answers. And remember that addition is commutative, so you could have things in different order, but be careful on your subtraction. Make sure that they're matching the way I have things written. Okay, so this one we're going to condense. So now we're going to use our properties and go backwards. So right here, I see I'm going to have to use my quotient property and divide the a and b. And here I'm going to have to use my product property. So I have to be careful. The first thing I'm going to do is bring those powers back up, though. So I'm going to use my power property and bring my exponents back up with my arguments. When you bring that 3 up, go ahead and leave it at subtraction. Don't bring up a -3. It just complicates things a little bit. So I have log base 3 of a to the 5th minus log base 3 of b to the 3rd plus log base 3 of c to the 1/3. Okay, so I'm going to remind you that c to the 1/3 is equal to the cube root of c. Back from algebra 2. Okay, so another thing you got to think about is the only reason I can apply these properties is because all of my bases of the logarithms are the same. If your bases were different, that's where your change of base formula would have to come in. You'd have to change them all to a common base first, then go back and apply your properties. Okay, so here I'm going to, what I like to do on these is I like to go off to the side, and I like to figure out my order of operations. What's going on with my a to the 5th, my b to the 3rd, and my c to the 1/3. So I go off to the side and calculate. So I have a to the 5th, subtraction is going to become division, b to the 3rd, and that's going to be a times, since this is addition right here, c to the 1/3, or the cube root of c. You don't typically see logarithms with fractional exponents. So you need to make sure you change those back to radicals. So right here, once I condense this log, that is basically going to be the argument of the logarithm. So now I just go back and I change it to my log base 3. And I create that argument that I just created over off to the side. A to the 5th times the cube root of c over b to the 3rd. Okay, so I do this because it helps me with my order of operations. If I had a bigger string of values there, things would get a little bit more complicated for me. So that's just a little trick that I've started using in my past years. All right, so one more. We're going to expand this logarithm. So this one is going to get just a little dicey. You have to be careful because you have a multiplication problem in the denominator. So first thing I'm going to do is I'm going to use my quotient property. And this is log base 10, so I don't have quite so much to write. Okay, so I'm going to have log x to the 7th power. I'm applying my quotient property. Quotient creates subtraction. So since I have that multiplication problem in the denominator, I have to be really careful and keep things grouped together. So now I'm subtracting that entire denominator log, which is going to be log z squared. And since this is a product, I can go ahead and separate that to addition, log, and I'm going to change my cube root of y to y to the 1/3. So I applied my quotient and my product. These brackets here are essential. Also remember the cube root of y is equal to y to the 1/3. So now I can go ahead and distribute my subtraction sign. And at the same time, I'm going to bring these powers down front to save myself a little bit of writing. So I'm going to have 7 log x minus, bring that 2 out front, 2 log z. I'm distributing a subtraction, so that's going to become a minus, and that 1/3 is coming out front. So 1/3 log y. You could rearrange it alphabetically if you wanted to, but there's really no need to. All right, so there's that one. You have a few of these to do, I believe, on a worksheet. So just make sure you're showing a couple steps on the harder ones if you want full credit on that assignment. Have a great day. I'm always here to help if you need me.